In this lecture, we will study about basic introduction to coordination chemistry. I'm Dr. Jinesh. I'm from Department of Chemistry, MS Ramaya, University of Applied Sciences. After this lecture, you will be able to differentiate double salts and coordination compounds, discuss Werner's theory of coordination compounds, define important terms related to coordination compounds, discuss nomenclature of the coordination compounds. First, we will study about double salts and coordination compounds and their differences. Addition compounds are formed when stoichiometric amounts of two or more stable compounds join together. Addition compounds are of two types. One, those which lose their identity in solution, we call them as double salts. Two, those which retain their identity in solution, and we will call here it as complexes. One example, KCl MgCl2 6H2O is a carbonylate, and K2SO4 Al2 SO4 thrice 24H2O alum are known as double salts, and CuSO4 4NH3 H2O tetramine copper 2 sulfate monohydrate and FeCN2 4KCN potassium ferrocyanide. These two are known as coordination complexes. Why? The difference is mainly based on the ions formed when these compounds dissolved in water. When crystals of carbonylate are dissolved in water, the solution shows properties of K plus ions, Mg2 plus ions, and Cl minus ion. In a similar way, a solution of alum shows the properties of potassium ion, aluminum ion, and sulfate ion. These are examples of double salts which exist only in the crystalline state. When the other two examples, tetramine copper 2 sulfate monohydrate and potassium ferrocyanide, they exist as distinct entities both in solid and in solution. Complex ions are shown by the use of square brackets. Compounds containing these ions are called coordination compounds. When these coordination compounds dissolve, they do not form simple ions. For example, this compound, this complex or this coordination compound, if it dissociates in water, we will not get any properties of copper ions. If this dissolves in water, we will not get any properties of Fe2 plus ions, or the existence of Cu2 plus ions and Fe2 plus ions in the solution will not be there. Compounds containing these ions are called coordination compounds. If these compounds dissolve in water, then it will form two types of ion that we will discuss in our coming sessions. Alfred Werner won the Nobel Prize for Chemistry in 1913 for explaining the bonding in coordination compounds. His main postulates are: in coordination compounds, metals show two types of linkages or valencies, primary and secondary. The primary valencies are normally ionizable and are satisfied by negative ions. The secondary valencies are normally non-ionizable. These are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number and is fixed for a metal. The ions or groups bound by the secondary linkages to the metal have characteristic spatial arrangements corresponding to different coordination number. We will discuss these points in the coming session. We will discuss about the valencies. The first valency, primary valencies. Primary valencies are non-directional. So primary valency will not determine the shape of the compound or complex. The complex commonly exists as positive ion. The primary valency is the number of charges on the complex ion. The complex CONH3C Cl3, not C3, Cl3, actually exists as CONH3 6 3 plus. So up to here 1 ion and 3 Cl minus ion. So we can see that this bracket, the portion or the group in this square bracket will be converted into a single ion and the remaining 3 chloride ions. Here, the negatively charged chloride ions, 3 chloride ions are there. So we call primary valency for this compound as 3 because it has 3 ionic bonds. Because as per the Werner's theory, primary valencies are normally ionizable and are satisfied by negative charge. We know that chloride ions, they are ionizable if they dissolve it in water. This complex will give you chloride ions and they are negatively charged. Here, in this case, they are negatively charged. Also, the number of chloride ions, here it is 3. So we will call it the primary valency as 3 for this complex. Secondary valency, these are directional. That means secondary valency determine the shape of determine the geometry or the shape of the molecule or the complex. The modern explanation would as follows. The complex commonly exists as, in modern terms, the number of secondary valencies equals the number of ligand atoms coordinated to the metal. This is now called the coordination number. Ligands are commonly negative ions such as chloride or neutral molecules such as NH3. Less commonly, ligands may be positive ions such as NO+. Each metal has a characteristic number of secondary valencies. In this example, CONH36Cl3, where 3 Cl minus are held by primary valencies and the 6 NH3 groups, which is inside that square bracket, are held by secondary valencies. Now we will discuss about few definitions of some important terms pertaining to coordination compounds. First one, coordination entity. A coordination entity constitutes a central metal atom. Here an example, here the central metal atom is cobalt, or ion bonded to a fixed number of ions or molecules. So it is fixed, it is bonded to a fixed number of ions or molecules in that entity. Is a coordination entity which the cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. Other examples are NiCO4. Here the central metal atom or ion is, here central metal atom is nickel and it is surrounded by with a fixed number of carbonyl group, 4 carbonyl group in this example. Another examples for coordination entity, PtCl2, NH3 twice, here FeCN6, 4 minus, CONH3, 6, 3 plus. So coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. Next is central atom or ion. In coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it is called the central atom or ion. So in the coordination entity, an atom or ion to which a fixed number of ions or groups are bound. So here you see, here in this example, nickel will be the central atom which is bound to ions or groups and form a definite geometrical arrangement. These central atom or ions are also referred to as Lewis acid. Ligands. The ions or molecules bound to the central atom or ion in the coordination entity are called ligands. These may be simple ions such as chloride, small molecules such as H2O or NH3, or larger molecules such as ethylene diamine, NCH2, CH2, NH2, or even macromolecules such as protein. When a ligand is bound to a metal ion to a single donor atom, as chloride, water, ammonia, the ligands are said to be unidentate. So when a ligand is bound to a metal ion through a single donor atom as with the chloride, water, or ammonia, the ligand is said to be a unidentate ligand. In didentate ligand, when a ligand can bind through two donor atoms, as in the case of ethylene diamine, there are two nitrogen atoms which can bond to the central metal atom. Or oxalate, where two donor atoms can be interacting with the central metal atom. Then this type of ligand is said to be didentate ligand. There is a symbol for density, Greek letter kappa, which simply describe how many atoms are bound to the metal. For example, ethylene diamine, it's didentate, so density is 2. So we will write that ethylene diamine is a donor capable of binding in K2 mode. There are different types of bidentate ligand or didentate ligand. It can be neutral or anionic. Examples are given for neutral ethylene diamine, bipyridal or 1,2-bis dimethyl phosphinoethane. In anionic bidentate, acetate, oxalate, acetyl acetonate, these are anionic bidentate. Next is polydentate ligand. When several donor atoms are present in a single ligand, as in the case of this compound, NCH2CH2NH2 thrice, the ligand is said to be polydentate. Another example is ethylene diamine tetraacetate ion, EDTA 4- is an important hexadentate ligand. Why we call it as hexadentate ligand? Because it has 6 donor atoms which can be interacting or which can be bonded through the central metal atom. It can bind through 2 nitrogen atom. It can bind through 2 nitrogen atom and 4 oxygen atom. 1, 2, 3, 4 oxygen atom to the central metal ion. Next is chelate ligand. When a di or polydentate ligand use its 2 or more donor atoms to bind a single metal ion, it is said to be a chelate ligand. The number of such ligating groups is called the density of the ligand. Such complexes called chelate complexes tend to be more stable than similar complexes containing unidentate ligand. So di or polydentate ligand, when they bond with which can donate more than 2 donor atoms, can form chelate when they are interacting with a single metal atom or ion. And these complexes will have more stability compared to the complexes containing unidentate ligands. Next is ambidentate ligand. Ligands which can ligate through 2 different atoms is called ambidentate ligand. Examples of such ligands are NO2- and SCN-. NO2- ion can coordinate either through nitrogen or through oxygen. Not both together, either nitrogen or through oxygen to a central metal atom. Similarly, SCN- ion, it can coordinate through sulfur or nitrogen atom. For example, for NO2-, if the bonding is happening through nitrogen atom in the NO2- group, then we will call that ligand as nitrito-N. Or if oxygen atom is involved in the bonding with the central metal atom or ion, then this NO2- group, this ligand, we will call it as nitrito-O, because through oxygen. SCN, if sulfur is interacting or sulfur is acting as the donor atom to the central metal atom or ion, then we will call it as thiocyanato ligand. If N is interacting or if N is the donor atom for the central metal atom M or ion, then we call it as isothiocyanato. Next, coordination number. The coordination number of a metal ion in a complex can be defined as the number of ligands, donor atoms, number of ligand donor atoms to which the metal is directly bonded. So one more time, the coordination number of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ions PtCl6 2- and NiNH3 4 2+, the coordination number of platinum and nickel are 6 and 4 respectively. Here 6, here 4. Similarly, in the complex ion FeC2O4 3 3-, CON3 3 3+, the coordination number of both Fe and CO is 6. Here we can see that only 3 ligands, but these ligands are didentate ligands. So 2 into 3, 6. Here also ethylene diamine, It is a bididentate ligand. So 3 ethylene diene means 3 into 2, 6 is the coordination number. Coordination number generally determines the shape of the complex. The shape of the complex is mainly determined by the coordination number. So there are some coordination number and their arrangement. There are some less common arrangement that we don't have to give more attention, but you can see if the coordination number is 2, the structure can be linear. If it is 3, then it can be trigonal planar. If it is 4, then tetrahedral square planar. If it is 5, then trigonal bipyramidal or square base pyramidal. If it is 6, it can be octahedral. If it is 7, it is pentagonal bipyramidal. If it is 8, then it is dodecahedral or square antiprismatic or hexagonal bipyramidal. If the coordination number is 9, it can be tricapped or trigonal prismatic. If the coordination number is 3, there is one more arrangement is possible, but it is less common, that is trigonal bipyramidal. For trigonal prismatic, this can less commonly seen in the compounds with in the complex with the coordination number 6. Next is coordination sphere. The central atom or ion and the ligands attached to it are enclosed in square bracket and is collectively termed as coordination sphere. The ionizable group are written outside the bracket and are called counterions. In the complex K4 FeCN6, the coordination sphere is here. The coordination sphere is FeCN6. Normally, coordination sphere we will put it inside a square bracket, and the counterion is K plus ions. Here K4, that means K plus ions are the counterions. So coordination sphere is a central atom or ion and the ligands attached to are enclosed in a square bracket and is collectively termed as coordination sphere. So in coordination sphere, central metal atom will be there as well as ligands will be there. Outside the coordination sphere, there will be counterions which can be positive or negatively charged. So coordination polyhedron. The spatial arrangement of the ligand atoms which are directly attached to the central atom or ion defines a coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. For example, CONH363 plus is an octahedral, NiCO4 is tetrahedral, and PtCl42 minus is a square planar complex. So in this session, we studied the difference between the double salt and coordination compounds is mainly based on the ions formed when these compounds dissolved in water. Alfred Werner won the Nobel Prize for Chemistry in 1913 for explaining the bonding in coordination compounds. Then we studied about few terms related to coordination compounds such as central metal atom or ion, primary and secondary valency, ligands and its classification into unidentate, adentate, polydentate. We studied about chelating ligands and amidentate ligands, the coordination number, coordination sphere, coordination polyhedron. Next topic is nomenclature of coordination compounds. At the end of this session, students will be able to perform nomenclature of coordination compounds. A complex is a substance in which a metal atom or ion is associated with a group of neutral molecules or anions called ligands. Coordination compounds are neutral substances in which at least one ion is present as a complex. These are the 2 points we have studied in our earlier classes. Rules for nomenclature. First, I will discuss the rules for nomenclature of coordination compounds. After that, we will take few examples and study how to name the coordination compounds. A. To name a coordination compound, no matter whether the complex ion is the cation or the anion, always name the cation before the anion, like how we name in ionic compound. First cation, second anion. That is, no matter whether the complex ion is the cation or anion, every time we should start naming cation first, followed by anion. In naming the complex ion, name the ligand first in alphabetical order, then the metal atom or ion. But when we draw the structure, always write metal atom or ion first, then ligands in the formula. But when you name the coordination compounds, name the ligand first in alphabetical order, then the metal atom or ion. So that is the difference when you name the coordination compound or when you write the chemical formula. These are the names of some common ligands. Anionic ligands: bromo, fluoro, oxo, hydroxo, cyano, oxalato, carbonato, acetato. Here we can see most of these anionic ligands, their names end with O. For example, here it is bromide, that became bromo. Hydroxide became hydroxo. Cyanide becomes cyano. Oxalate become oxalato. So anion name ends with O. Neutral ligands: ammonia will be known as amine, water as aqua, NO as nitrosyl, CO as carbonyl, oxygen as dioxygen, N2 as dinitrogen, C5H5N as pyridine, and the famous didentate ligand H2NCH2CH2NH2 ethylene diamine. So these are the name of some common ligands which appear in coordination compounds. Again, I am repeating the things that we studied as the name of the anionic ligands and neutral ligands. For anionic ligands end in O. For anions that end in ide, the anions that end in ate or ide, change the endings as follows. For example, if it is bromide, it will be bromo. If it is sulfate, it will be sulfato. If it is nitrite, it will be nitrito or nitrito. For neutral molecules, the common name of the molecule is used. For example, ethylene diamine. But water is called aqua, ammonia is called amine, carbon monoxide is known as carbonyl, nitrogen and oxygen are called dinitrogen and dioxygen. Now, based on the number of ligands in the complex, Greek prefixes are used to designate the number of each type of ligands in the complex ion. For example, same ligand, two molecules of or two ligands are there, then we will call it as di. If 3 are there, tri. If 4 are there, tetra. Now, if the ligand is a polydentate ligand, then we will use, instead of di, tri, tetra, we will use bis, tris, tetrakis, pentakis instead of di, tri, and tetra. It's given here. If one ligand group is mono. If the same ligand repeated twice, then it will be di. If it is a polydentate, instead of di, we will use bis. If it 3, then tri. For polydentate, we will call it as tris. For 4, tetra, tetrakis. Penta, for polydentate, pentakis. Hexa, for polydentate, hexakis. Hepta, octa, nona, deca, undeca, and dodeca. These are the numerical prefixes which we should put in front of the name of the ligands based on how many molecules or how many ligands are present in that structure. After naming the ligands, we have to name the central metal. If the complex ion is cation, then the metal is named same as the element. For example, in a complex, cobalt is the central metal atom or ion, and the coordination, the complex ion is cation, then the metal will be called as cobalt. If platinum is there, we will call it as platinum. Now imagine your complex ion is an anion, then name the metal ends with the suffix ate. For example, we have a cobalt containing complex ion which is an anion, then the name metal cobalt should be named as cobaltate. If it is platinum, it will be platinate. If it is Fe, if Fe is present in the complex ion as cation, then we will use the name iron. But if Fe is present in the complex ion as anion, and the complex ion is anion, then we will use the word ferrate, not ionate. That we should keep it in our mind. Following the name of the metal, the oxidation state of the metal in the complex is given as in Roman numeral in parentheses. For example, you have a complex CONH3 6. You have a complex ion like this. So we have to find what is the oxidation state of cobalt. If it is 3, we will write a Roman letter 3 just after the name of the metal atom or metal ion. So we'll write cobalt 3. For historic reason, some coordination compounds are called by their common names. FeCN6 3- and FeCN6 4- are named ferricyanide and ferrocyanide respectively. And FeCO5, we will call it as iron carbonyl. This is mainly due to the historic reasons. So we will call by their common name. So we will do some examples where we will name the complexes. The first one, Cr, NH3 thrice, H2O thrice, and Cl3. So before starting how to write the name of the complexes, first we have to find whether the complex ion, so here this is the complex ion. So this complex ion is cationic or anionic. We know that from the structure itself, we know that it is cationic in nature. If it is cationic in nature, then we can start the name with this cation. After that, we will write the anionic part, which is chloride. So, first point, we now know whether we have to write the complex ion first or the anion first. We now know that we have to write the complex ion first. CrNH3 thrice, H2O thrice. First, we have to write the name for the ligands first. 2 ligands are there. One is ammonia. Ammonia we will call it as amine. And H2O we call it as aqua. So, if you alphabetical order, A, both are starting with A, but amine M and water Q. So M comes first before Q. So definitely first we have to write amine. How many amines are there? 3. 3 means tri. So we should start with the triamine. Triamine we should start. Then water. Water, the ligand name is aqua. How many aqua groups? 3. So it is triaqua. Triaqua. After that, we have to write the name of the metal. Metal is chromium. Here, the chromium is part of the complex ion, which is cation. So we can write the name as such. No issue. Chromium. Next step, we have to put the Roman letter based on the oxidation state of chromium. So how we will calculate the oxidation state of chromium? I will be teaching you that the next. Chromium, we don't know the oxidation state, so we will give the value X. Ammonia doesn't have any charge. 3 ammonia groups are there. So the total charge from ammonia is 0 into 3. Plus water doesn't have charge. Total 3 water is there. Plus how many Cl3? 3 Cl3. We know that the charge of one chloride is -1. This one equal to 0. So total it should be 0. So from this we know that X will become +3. Because this is 0, 0. So X minus 3 equal to 0. So X equal to +3. So +3 means we have to put the Roman letter 3. After that we have to write the anion name. Anion is here chloride. We don't have to give the number how many chloride is required in the structure. No need to require. Just write chloride. So the name of the complex is triamine, triaqua, chromium 3 chloride. We wrote the name. Similarly, we will be able to write the name for the second compound, that is platinum NH3 5 times Cl Br3. First, we have to check whether the complex ion is cation or anion. It's cation, because normally when we draw the formula also, cation we will write first. So the complex ion means which is in the bracket. This portion is the complex ion part. That complex ion part is cation, so we have to name it first. In that complex ion, we have to write first the ligand. How many ligands are there? Two types of ligand. One is amine, second one is chloro. So as per the rule, alphabetical order, A should come first. So amine we should write first. How many amine groups? 5. 5 it is penta. So we should start with pentaamine. Next is chloro. How many chloro is there? 1 is there. So we can write monochloro or just chloro. Pentamine, chloro. And we know that this platinum belongs to the complex ion, which is cation. So we have to just write the name of the metal, that is platinum. Then we should write the platinum oxidation state. How we will calculate the oxidation state of platinum? Platinum oxidation state I don't know, that is X. Plus ammonia doesn't have any charge. Total 5 ammonia is there. Plus chlorine is having a charge of -1. 1 chlorine is present. Plus Br3. So total -1 into 3. So total it should be 0. So if I calculate, so I will get X minus 4 equal to 0. So X equal to 4. So oxidation state of X, that is platinum, should be 4. So I have to put the Roman letter based on the oxidation state of platinum. Then I have to write the anionic part, which is bromide. So the name is pentamine chloro platinum 4 bromide. Pentamine chloro platinum 4. Third compound, platinum H2N CH2 CH2 NH2, that is ethylene diamine, Cl2 and Cl2. We have to find whether the complex ion is cation or not. Yes, it comes first, so it's cation. So in cation, we have to write the ligands first. 2 ligands, ethylene diamine and chloro. So ethylene diamine starts with the E, chloro starts with the C. So alphabetical order, C should come first. So we should write chloro first. How many chloro group? 2 chloro group. So we should start with the dichloro. Now we have to write ethylene diamine. 2 ethylene diamine is there. Ethylene diamine we have to write as bis, because it is didentate. If its density is more than 1, so the number will be bis, tris, like that. We have studied that. So bis ethylene diamine. Bis ethylene diamine. Ethylene diamine we can put it in a bracket. So all ligands over now. We wrote for chloro and we wrote ethylene diamine. Now next is platinum. Platinum is part of the complex ion, which is cation. So we can write platinum as such. Now cation is over. Next step is we have to put its oxidation state. How to calculate the oxidation state, that I will show you now. Platinum, we don't know what is oxidation state, that is X. Ethylene diamine doesn't have any charge, so charge is 0. How many ethylene diamine group? 2. Plus chlorine is having a charge of -1. How many chlorine group? 2. Plus Cl2. Cl2 is 1 Cl is -1 -2 equal to 0. So if I count, it will be X minus 2 equal to 0. So X equal to plus 4. So X equal to plus 4. So I have to write the oxidation state of platinum as 4. Then the anionic part is chloride. Anionic part is chloride. So we finished now 3 examples. The next example is cobalt, then ethylene diamine thrice, then 2 SO4 thrice. SO4 thrice. We'll start. First, whether the complex ion, that part is cationic or not? Yes, it is cationic. So if it is cationic, first we have to name the cation first. So for that, in cationic part, first ligand should come first. Only one ligand is present, that is ethylene diamine. 3 ethylene diamine is there. If 3 ethylene diamine is there, ethylene diamine more than density 1, so it should be not tri, it should be tris. So tris ethylene diamine. Tris ethylene diamine. Close it. So we finished now ligand part. Now next is metal cobalt. Now the cobalt is part of the cation, so we can write cobalt as such. Now next step, we have to give the oxidation state. How to calculate the oxidation state? For cobalt, I don't know the oxidation state, that is X. Ethylene diamine doesn't have any charge, so 0 into 3, right? Three. Now how many complex ionic part is there? That is 2. So 2 means you have to multiply these things with 2. Plus SO4 is having -2 charge, -2 into 3 equal to 0. From this you have to find what is the charge of X. We will get X as +3. So we have to give the oxidation state of cobalt as 3 here. Now the anion is sulfate. Why we multiplied this X plus 0 into 3 with 2? Reason is this complex ion, two numbers are there, that's why. Next is K4FeCN6. Here the complex ion is anion, and this is the counter ion, which is a cation. So we have to write cation first. So we should start with the cation, which is potassium. So we'll write potassium first. Now we have to write the name of the complex ion, which is an anion here. In anion or cation, first we have to name the ligands. How many ligands are there? Only one type of ligand, that is cyano. How many? 6. So potassium. If it is 6, we will use hexacyano. Now we have to name the metal atom or ion. Now the metal atom ion is part of the anion. So instead of writing iron, we have to use ferrate. It will end with 8, ferrate. Not over, we have to put the oxidation state. How to calculate oxidation state? Now I will teach you. Potassium, we know that potassium charge +1. How many are there? +4. Plus Fe, we don't know, that is X. Cyanide, it is -1. Similarly, 6 is there, equal 0. So from this, if I calculate, I will get X as +2. So I will give the oxidation state in the Roman numeral after that. So the name potassium hexacyanoferrate 2. Next example, Na2NiCl4. Again, the coordination complex part, which is anionic. So first we have to give the cation name. Cation is sodium. So we have to give the name for sodium first. Then the complex ion. In complex ion, first we have to write the name for the ligand. Ligand is chloro. Total 4 chloro groups are there. So it should be 4 means di, tri, tetra. So it should be, we should start with the tetra. Tetra chloro. Now next we have to write this central metal atom or ion. Now this metal atom or ion, which is part of the anion, so it should be not nickel, rather nickelate. Not over, we have to put the oxidation state. We'll calculate the oxidation states. For sodium, 2 are there. We know that sodium is having an oxidation charge of +1. Nickel, we don't know, X. Chlorine, 4 are there. Each one have -1 charge. So here total 0. So X, if I wanted to calculate, I will get X as 2. So if I am getting X as 2, I have to put that as numeral, Roman numeral after the name of the metal. So I wrote 2. Next example, PTNH3 twice Cl2. PtNH3 twice Cl2. How we will name the complex? So I am splitting it. Sorry. You see the structure now. Only the complex ion part or complex is present. There is no counter ion in this structure. It's neutral, no requirement of any counter ion. So in this kind of coordination complex, how we will name? So definitely there is no cation and anion here. So we will take this as a single entity and will name this entity. There is no counter ion, there is no anion or cation. We will start the naming. So platinum is the central metal. Ammonia and chlorine, both are the ligand. Ammonia is amine, starts with A. Chlorine, chloride or chloro, it is C. Obviously, we should start with amine. Total 2 amines are there. So if it is 2 amine, we will write diamine. Now chloro, 4 are there. So 4 means tetrachloro. Now platinum. Not finished. We have to put the oxidation state of platinum. I'm giving the platinum oxidation state at X. Ammonia doesn't have any charge, but chlorine we have -1 charge, 0. So X should be +4 as per the calculation. So I have to put that oxidation state after we write the name of the central metal atom, which is platinum. Next is FeCO5, single entity, no cation, no anion. We have to just name this complex part. So ligand is carbonyl, total 5 carbonyls are there. So we will write pentacarbonyl. So ligand got over, now the metal is iron. And we have to give the charge. X plus carbonyl doesn't have any charge, so X will be 0. So here the oxidation state of iron is 0. Next example, NH4 twice, NiC2O4 twice, H2O twice. So here if you see the coordination complex ion part is anion and ammonia group is cation. So how we will write the name? First we will write the cation name. Cation is ammonia. So ammonium. Next we have to write the anionic part. In anionic part, first we have to write the ligand. 2 ligands are there. One is oxalato, one is aqua. Obviously aqua we should write first because as per the alphabetical order. How many aqua group? 2. So 2 means diaqua. Oxalato 2. Oxalato we know that it is a density is 2. So we have to write instead of di, we should write bis. Bis oxalato. Now the metal is nickel, and nickel is part of the anion. So it is nickelate. Not over, we have to find its oxidation state. How we will find the oxidation state? That we will study now. Ammonium, we know that it is having a charge of +1. So how many are there? 2. Nickel, we don't know the charge, X. But total 2 nickels are there. So it will be 2X. Plus oxalate, we know the charge as -2. So -2 into total 2 into 2. Sorry, here only 1 nickel is there. So X. -2 into 2 plus water doesn't have any charge, 0 into 2. So total it should be 0. So from this we can calculate the X value. We will get X value as +2. If you solve this, then that value of 2 should be given as a Roman numeral just after naming the metal ion. Another example, AgNH3 twice, AgCN twice. Here both cation and anion, both are complex ion. So among this, which one is the cation? Cation is this part that we have to name first. How many ammonia group? 2 ammonia group. So it is diamine and silver. Here I don't have to write the argentate because here the silver is a part of the cation. So we will write silver. And the second complex ion, which is anion. So anion should come after the cation. So here in this anion, 2 ligands, dicyano. Only one ligand is there, that is cyano. 2 cyano groups are there, so dicyano. Now the silver is part of the complex ion which is anion in nature. So we should write argentate, and both their oxidation state we are writing as 1. Now reverse. If we get the name of the coordination complex, whether we will be able to write the structure or the formula of the coordination compounds. So conversion from the nomenclature or the name to the formula. Hexamine iron 3 nitrate. Hexamine iron 3 nitrate. So in this structure, first we have to write the cation, then we have to write anion. In cation, in the formula, first we have to write the metal. Reverse. Then we have to write the ligand. Only one ligand is there, that is ammonia. How many are required? Here is a hexamine, so NH3, 6. So we finished the cation. Now we have to write the anion. Anion is nitrate. But this is not complete because we don't know how many counter ions are required. How many counter ions are required to satisfy the oxidation state of Fe. So here oxidation state of Fe is given, that is 3. So that is 3 plus ammonia doesn't have any charge, so 0 into 6. So the complex ion, that is the cation part, is having a charge of plus 3. To satisfy that, NO3 also should have a minus 3. But we know that NO3 is only minus 1. NO3's charge is minus 1. So to tackle this, how many nitro group should be there to get minus 3, which will satisfy the plus 3 oxidation state, plus 3 charge from the complex ion. We know that minus 1 to minus 3, we have to multiply it with the 3. So total 3 nitro group should be there in the formula. So the formula we will write it like this: Fe NH3 6 and NO3 thrice. Next one, ammonium tetrachlorocuprate 2. Ammonium tetrachlorocuprate. First is cation, that is ammonium. First we will write it here. We will know, now we don't know how many ammonium counter ion should be there. We don't know. Next is anion. Now anion is the complex ion, so we have to put it in a bracket. Tetrachlorocuprate. So first we have to write the metal, that is copper. Tetrachloro means CuCl4. Now CuCl4, and they have given the oxidation state of copper as 2. So now from this we have to find how many ammonium group should be present in the formula. So CuCl4. So we know that first we will find the charge of this complex ion. Copper is having now oxidation state of 2. Chlorine is minus 1. Minus 1 into 4. So 2 minus 4, that is minus 2. So the total charge of this complex ion is minus 2. And we know that ammonium is having a charge of plus 1. So in order to satisfy minus 2, total plus 2 should be there from ammonia side. How to get plus 2? We require 2 ammonium group, because 1 ammonium will give plus 1, 2 ammonium will give plus 2. Then it can satisfy the charge obtained from CuCl4. So the structure of the compound is NH4 twice CuCl4. Next is sodium monochloropendacyanoferrate 3. Sodium monochloropendacyanoferrate 3. How we will write the formula of this compound? Sodium monochloropendacyanoferrate. So here sodium is the cation, which is the counter ion. First we are writing sodium. We don't know how many sodium is required. Next is our complex ion. Complex ion is a cation here. So complex ion, cation, which metal? Fe. First we have to write Fe. How many ligands are there? Monochloro. Chlorine is present. Pendacyano. Cyanide is present. So monochloropendacyano. So cyano, how many? Cyano 5. Chlorine 1 because it's monochloro. Finished. Structure is finished. But still we have not checked whether the counter ions numbers are correct or not. How we will do that? Fe, now we know that its oxidation state is given, that is 3. Cyanide -1 of +5 plus chlorine, that is -1 of 1. So what is the charge of this complex ion? Now we were calculating and we found that it is 3 + -1 into 5 + -1 into 1. That is the total charge of the anionic part. So 3 - 5 - 1. 3 - 5 - 2 - 2 - 1 - 3. So -3. So in order to counteract that -3, sodium should provide +3. But one sodium atom or ion will provide only +1. So total 3 sodium ions should be present as counter ion. So the formula will be Na3 FeCN5Cl. Next is potassium hexachlorocobaltate 3. Potassium hexachlorocobaltate 3. Here cation, anion. Here anion is the complex ion. First we have to write the name of the cation, which is potassium. So we put potassium symbol, but we don't know how many potassium counter ions should be there. That we can see only after checking the charge of the ligands and the central metal atom or ion in the anionic part, which is the complex ion. So hexachlorocobaltate 3. So we require the central metal atom, that is cobalt. So cobalt we wrote. Hexachloro means Cl6. Not got over. We have to find how many counter ions are present. For that we have to find the charge of this anion. So cobalt is having a charge of 3. It is given here. 3 plus -1 into 6 because chloro group is having -1 charge. So total is 3 minus 6. 3 minus 6 is -3. In order to counteract this -3 charge of this complex ion, potassium should provide +3. But we know that potassium is having +1 for a single atom or ion. So here it will be how many potassium ions are required? 3. So the formula will be K3COCl6. Now we studied how we will change the formula into the nomenclature, name of the complex, then reverse. From name of the complex, how to find the formula of the coordination complex. This much we studied. And now you can do the practice problems. Name the following compounds: COBr NH3 5 times SO4, FeNH3 6, CrCN6, COSO4 NH3 5 plus, FeOH H2O 5 2 plus. So these formulas you should convert it into the nomenclature. We have to find the name of this complex. Opposite. Write the formula of the following compounds. Name of the complex is given. We have to find its formula. So both these sessions we studied already. So you will be able to perform these practice problems. Another examples. Write the formula of the following compounds. Tetramine diaqua cobalt 3 chloride, potassium tetracyanonickelate 2, tris ethane 1,2 diamine chromium chloride, amine bromido chlorido nitrito and platinate 2, dichloro bis ethane 1,2 diamine platinum 4 nitrate, iron 3 hexacyanoferrate. So these compounds also you should be able to write the formula. Another practice problem, we have to name the following compounds: CONH3 6Cl3, CONH3 5Cl Cl2, K3FeC2O4 thrice, K2 palladium K2PD Cl4, K3FeCN6, PTNH3 twice Cl NH2CH3Cl. So these are the practice problems that you can actually perform yourself after learning the initial portion of this lecture.